So the overall topic today is really about how historically and I guess going forwards we think about constructing reaction mechanisms. So far I've talked, I suppose, about populating the reaction mechanisms with parametric data. And now I'm going to think about how we might put reaction mechanisms together for different applications. And as part of that, we'll be looking at least for some examples, what are the important reaction classes that we see under low temperature conditions, for example, that might drive ignition, or under high temperature conditions that might drive flame behavior, and how they might vary for different fuels. Because what we'll see is a lot of the work that historically has gone into ways to construct reaction mechanisms has been carried out for the simplest type of hydrocarbon fuels, which are alkanes. And as we're looking at alternative fuels for the future, then these are more complex in terms of the fuel structures, in terms of the functional groups that they contain. And so we might have to make some developments in the techniques that we've got to construct reliable mechanisms for new fuels. So, I mean, historically, this has, of course, been a human endeavor, really. So there are, many scientists who've worked in combustion. I mean, going all the way back to Semenov, Zeldovich, who've thought about the chemical kinetics of combustion. And then I think probably in terms of protocols of developing reaction mechanisms, we can look at labs like Lawrence Livermore. I'm thinking of Charlie Westbrook, Bill Pitts, people who are there, who've got that long time chemical expertise. And so they know by looking at a fuel or a fuel oxidizer system what types of reactions would be involved, and actually probably even have a feel for how to populate reaction rate data. And so, historically, this is developed through human expertise. And the process involves, selecting your important reactants and products, and then thinking about what intermediates are going to be formed as we go from reactants to products. And we'll see that for complicated hydrocarbons, there are a huge number of intermediate species in these mechanisms. And some of them are necessary in terms of predicting key production rates and all the key quantities that we want to be able to simulate. So, at a fundamental level, that might be things like ignition delays, flame speeds. We might want to look at things like extinction, for example, in practical devices. We might want to understand instabilities, oscillations, etc. So then, using chemical expertise, we need to think about the types of reactions that can occur between these couple groups of species. And then, of course, we need reaction rate data for all of those, Arrhenius-type expressions or pressure-dependent expressions. And we need thermochemical data. And I think, actually, as people who use models, we perhaps neglect really to think about thermochemical data more than we should. So I'll show some examples that will be a warning there. So over time, experts in the field have developed, I guess, what we call protocols for different types of application. And these are kind of, I suppose, in the formation of reaction classes that might be relevant for a specific fuel type under different temperature pressure conditions. And so, I don't know how many of you use the reaction mechanisms that come from sites like Lawrence Livermore, but over the years, they've developed mechanisms for more and more complex fuels, starting probably with hydrogen, moving up to syngas, methane, and now gasoline surrogates, diesel surrogates, and surrogates for biofuels. And I think on the very first day I showed how the size of chemical mechanisms has grown over the years. So to simulate a surrogate biofuel, we might be looking at hundreds to thousands of species and thousands of reactions. So if we did this in kind of a combinatoric way, so if we had all our reactants, products and intermediates, and we allowed every reaction to take place with all of those species, then we'd end up with a kind of explosion in terms of reaction numbers. And so typically, protocols are developed really to ignore reactions if the rate is very slow compared to the overall time of interest, to leave reactions out if they're too endothermic, or the reaction might be too complex to take place in reality, so too many bonds have to be broken or too many products have to be formed. And sometimes we ignore pathways to minor products as well, and that stops the size of the system getting absolutely huge. So over the years then, we've developed this concept of reaction classes. A good reference for reading about this is the Clean Combustion book, which I think, or there's a chapter in the Clean Combustion book, which I plugged, I think, on day one. They talk about the development of reaction classes. These are used in the human generation of mechanisms, but also, once we understand reaction classes for different types of fuels, we can try to automate that by including those reaction classes in automatic mechanism generation. So doing it using the aid of a computer. But obviously, automatic mechanism generation is only as good as our knowledge of the reaction classes and the data that we've got to populate those reaction classes in terms of reaction rates and thermochemistry. So the reaction class is basically a kinetic generalization that will embody analogies and physical principles that we need to use to estimate rate constants. So I talked a little bit about this already, but we might have very detailed experiments and very detailed calculations for smaller fuels. And what we want to do is to encompass that information to be able to estimate reaction rates or thermodynamic data for larger fuels that follow the same reaction classes. So, taking alkanes as an example, we might have detailed data, say for propane or maybe even butane, but we might want to do some simulations for alkanes that are C16, C20, and we're not going to be able to theoretically calculate those rates. So can we develop systematic ways, reaction rate rules based on reaction classes to estimate that data for larger molecules of interest? So a reaction class, well, first of all, it's going to have a pattern or rule that recognizes the chemical reactants. So it might say, okay, oh, this is the fuel, this is a radical OH, and so that reaction class would be hydrogen abstraction, for example. Then it needs an actual reaction, so transformation about how the specific reactants will be converted to products. And then it needs to make some estimates of the rate constants associated with the transformation. And this is generally built up from years of chemical experience from many people who've worked in the field. We can get assistance. More recently, there's been techniques to give assistance through computational approaches. I mean, Kimbot is one example here, using a chemical network approach that will try to estimate what the potential energy surface is for a reaction sequence. But even Kimbot actually has embedded in it some rules about reaction classes to help it to find the right pathway through the reaction network. So some examples then. We tend to split these into high temperature and low temperature reaction classes actually. And there is some overlap obviously, but we'll see that later on today, we'll come to look at some sensitivity analysis, that there really are differences in terms of the important reactions that take place within different temperature regimes when we're simulating combustion problems. So examples of high temperature reaction classes would be, for example, the unimolecular decomposition of the fuel, the hydrogen abstraction from the fuel via various different radicals. I mean, the one we'll see which crops up most commonly is hydrogen abstraction by OH. So that would be pulling a hydrogen off the fuel, forming an alkyl radical, which will then go off and down further into a reaction sequence. So at high temperatures, we might see that alkyl radical decompose. We might see it isomerize, so internally reorganize to give us another species, etc. Okay, so either a human expert or an automatic mechanism generation code looking at high temperatures would be looking through each of these reaction classes and working out whether they're physically sensible for the problem and whether to include them in the reaction network. Oh, okay, I had some animation here. So that's exactly what I've just said, I think. Low temperature chemistry is actually more complex. I don't know how many of you are familiar with low temperature chemistry routes, some of you probably. So this hopefully will be familiar to some of you, but if you haven't seen these routes before, then there's quite a lot of reactions in the low temperature reaction classes. So I think the thing to pull away from this is that actually at low temperatures, we've usually got this competition between chain branching routes and routes that might lead either to radical chain propagation or to radical termination. And so if the chain branching routes win out, then we tend to see ignition and combustion occurring, whereas termination routes win out, then we tend to see a slowing down of the reaction. So I think I gave a simple example of chain branching in the hydrogen system, but for hydrocarbons, it's a little bit more complicated. So let's say we've abstracted a hydrogen from our fuel, we've formed an alkyl radical, and then the low temperature route would be an addition of oxygen to that alkyl radical to give us a peroxy radical, the alkyl peroxy radical here, RO or RO2, sometimes called RO2. So I'll go through the chain branching route first, and then we'll look at some of the competitive reactions here. So if we are under favourable conditions for ignition, then the next stage would be the isomerization of that alkyl peroxy radical to give us a hydroperoxy alkyl radical, which we shorten to QOH. And there's lots of reaction pathways for QOH, but the one which is going to lead us to chain branching is the addition of oxygen to the QOH to give us O2QOH, and then the isomerization of that, followed by the formation of a ketohydroperoxide plus the OH radical. So we started out with an OH radical that was abstracting a hydrogen from the fuel. We've got one back here, but then the ketohydroperoxide can also decompose to give us a second OH. So it's complicated, but it's still a classic chain branching route. We start out with one OH, and at the end of this low temperature branching sequence, we've got two OHs back, and so that's a chain branching route which will accelerate combustion. But we've got competitive reactions going on all the way through this chain. So RO2, this is a reversible reaction. Under certain conditions, the reverse rate can be important, and it can go back to form the alkyl radical. The alkyl radical can react with RO2, it can react with HO2, react with methyl peroxy radical. RO2, an important one that we'll see crops up later is the concerted elimination of an alkene plus HO2 from RO2. And so this is effectively a termination reaction because HO2 is much less reactive than the OH radical that we started with. And so that's one of the competitive routes that would lead to a slowing down of combustion. And we've also got competitive routes following the isomerization to QOH. We can form a cyclic ether plus OH. So that would be a propagation route because we started out with one OH radical and we've got one back. If we form an alkene plus HO2, that would slow the reaction down because HO2 is less radical, etc. So even for simple alkanes, the low temperature chemistry, there's a lot of different reaction pathways. And if you can imagine, we need reliable rate data for each of these reaction classes that we can extrapolate to larger fuels. And we also need reliable thermochemistry data, particularly, I would say, for some of these intermediate species like RO2 and QOH. And that's somewhat difficult to achieve for larger molecules. Okay, so whether or not that makes sense at this stage, we will be coming back to this low temperature chain branching several times because these reactions crop up in many systems. I just put a nice example here to sort of try to link a bit to the first 2 days. So this is an example of isomerization on the left. So this is the rearrangement of our peroxy radical to give us QOH. So we actually form a ring at the transition state, and then the ring opens, and we form the hydroperoxy alkyl radical here. And the one on the right is the elimination of OH from O2 QOH to give us a keto hydroperoxide and the OH radical. So again, there's a ring formed at the transition state. So if we've got information, for our smaller molecules, how can we try then to use that to give us useful reaction rate data for our larger molecules? And we use the concept of a functional group. So again, I'm sticking to alkanes just for now because it's easier, but we will look at some other examples later. Oh. Okay, white on pale blue doesn't work very well, unfortunately. So if we're thinking here about a reaction class of a hydrogen abstraction to start with, then we've got hydrogens of different types here because of the type of carbon that they're bonded to. So here, for example, we've got a primary carbon because it's only bonded to one other carbon. This should say secondary, although you can't see it very well. This is a carbon bonded to two other carbons, and then we have a tertiary carbon bonded to three other carbons. And these are all classified as different functional groups. And in fact, the bond energies between the carbon and the hydrogens for each of these different functional groups will differ. And that will affect the rate at which we can pull a hydrogen off any of these carbons. So it will affect the rate of hydrogen abstraction. So, for example, a radical on a carbon atom is more energetically stable for a tertiary carbon than it is for a primary carbon. So that means that for alkanes, a tertiary hydrogen atom is more easily extracted from the carbon atom than for a primary carbon, for example. Okay, and so we have data for small molecules which gives us the relative rates for these different functional groups. And then as we go to longer and longer carbon chains, we can still apply the same concepts because we've got the same bond energies for the same functional group, even if it's in a different molecule. Okay, so we can extrapolate our information. So here's an example of hydrogen abstractions by various different molecules. So in the combustion examples that I'm going to show, we're most likely at low temperatures to see the importance of hydrogen abstraction by OH. And we've got basically Arrhenius parameters here for the different functional groups, whether we've got primary hydrogen, that means a hydrogen attached to a primary carbon, or a secondary hydrogen or a tertiary hydrogen. We may also see at intermediate temperatures the importance of abstraction through HO2, and at high temperatures maybe by H. Okay, so we've got, for alkanes, we've actually got quite good data on these functional groups. So I'll come back to this concept later when we talk about oxygenated fuels. Okay, so that's sort of introducing the concept of reaction classes. So how do we go about formulating a mechanism for a larger fuel or even for fuel mixtures? Reaction classes can vary with temperature, so I showed you high and low temperature reaction classes. And so the size of the mechanism will depend on whether you want a mechanism which is general, which you can use over a very broad range of temperatures and pressures, or whether you might specifically want a mechanism that's smaller but is only really going to be used at high temperatures. So if you're pulling mechanisms from the literature to use in your models, always check, was the mechanism intended to be just for high temperature problems, or is it intended to be general? Because actually sometimes you see comparisons in the literature where people have taken a high temperature mechanism and gone, oh, it doesn't work for ignition delays. Well, you know, no surprise, because it never was intended to include low temperature chemistry. Okay, so that's one point to make. I guess the second point to make is that we tend to build mechanisms in a hierarchical way. We would start, for any hydrocarbon mechanism, of course, contains the hydrogen-oxygen scheme and also contains the CO-hydrogen scheme, etc. And so we're building up the mechanism, starting with a base mechanism, which is for hydrogen and maybe C1 to C4 chemistry. Then we're going to add in there a primary mechanism, which is describing the initial fuel and the reactions of the initial fuel and the directly derived fuel radicals. Okay, so we might want to include quite a lot of detail there. And then for larger hydrocarbons, we might have a secondary mechanism. So as the larger molecules break down through the degradation sequence, they may form secondary species. And these may be less important in terms of driving the combustion behavior, and so we might here want to carry out some simplifications just to stop the mechanism from exploding to become a huge size. Okay, so the base mechanism would tend to be very specific reaction rate constants. So from small molecules, we probably will have good data from either measurements or from theory. For the primary and secondary mechanisms, then, we will, for larger fuels, if it's a new mechanism, be looking to use this concept of reaction classes to define how our fuel is going to oxidize. So it's quite a nice schematic diagram here from Matteo Paolucci, just showing the hierarchical development of mechanisms. So at the very base of all mechanisms, you've got the hydrogen-oxygen scheme. And I think I might have mentioned this yesterday, but we'll see that there is usually, particularly at high temperatures, for any fuel, some sensitivity to reactions in this scheme. And then we're building up to include CO. So we've got a syngas mechanism there. Then we're building up to include methane, C2, C3, C4, and up to, well, in this case, this is a fossil fuel mechanism in the middle. But actually, you know, we might want now to develop mechanisms for alternative fuels. So we might actually want to go in the direction of including alcohols or biodiesel surrogates or phenolics. And then on the right, you know, depending on what we want to do with our mechanism, if we want to predict pollutant formation, then we might have to have a sub-mechanism which describes NOx formation, or we might be interested in the sooting index, so we might want to predict aromatics and PAH formation. So you can see how mechanisms grow in size to develop to include thousands of reactions. So, I mean, after all these years, you'd think we would just have a standard base mechanism that everybody uses, right? Maybe not quite the case, but I would say that probably in combustion now, the most commonly used base mechanism, which gives us the chemistry for the hydrogen in this up to maybe C3, C4, is probably the Aramco mech, which comes from NUI Galway. Has anyone got any experience of using Aramco mech? Yeah, a few people. So this is probably the most up-to-date mechanism. So the small molecule chemistry is usually, even if it's not the Aramco, it's usually a fairly well-validated, detailed mechanism of the smaller species. Here, reaction rate data tends to come from measurements or high-quality theory from databases. So there would be far fewer estimates of rate constants in the base mechanism of your scheme. What this means is that the small molecule chemistry should be known with a much lower uncertainty than if we're developing a new mechanism for the primary fuel part of our scheme. The caveat that I would place here is that actually if we're using what I would call maybe, I don't know if the word legacy mechanism is a little bit unfair, but if you're using a mechanism from the literature that's quite a number of years old, it may well be that the base chemistry has not been updated, and so potentially could be out of date with respect to new measurements and new theory calcs. But I would advise extreme caution in going, oh, okay, well, I've downloaded this mechanism for my huge fuel. I think I will just tidy it up by replacing the base mechanism with the latest version of a Ramco mech, and that will improve my simulations. I would be careful about doing that because for large fuels, some of the mechanisms may have been tuned to fit towards certain experimental data sets, and that tuning will be dependent on the base mechanism that was there when the mechanism was built. So you might find that by swapping the base mechanism, you can create problems in the overall scheme. So that's, you might find it not, but it's just something to watch out for. Usually when mechanisms are posted, they are a complete quantity. I don't know if anyone's got any experience of doing this, but they're kind of interdependent often. I mean, at some point we can have a discussion around how we should improve mechanisms and whether tuning rate constants is the way to do it or not. It's not something I'm a massive fan of, but I think if you're starting with a new fuel and you're constructing a mechanism for a new fuel, often it's just necessary to do that, right, to make any sense of your predictions. Anyone got any comments about that? Okay, so a little bit more detail about Aramco. So this is a C1 to C4 mechanism that has been developed in a hierarchical way from the bottom up. So starting with hydrogen-oxygen submechanism, and then a C1 submechanism was added. And over the various different versions, we're probably, I don't know, we might be up to higher than 2 now, but it's included carbon species up to C4. And actually, the advantage of this mechanism is there's been a huge amount of effort to validate it against pretty large array of experimental measurements for many fuels, including data from shock tubes, rapid compression machines, flames, jet stir reactors, plug flow reactors. So it's comprehensive. It has been evaluated in quite a lot of detail, and it's probably the best place to start for a sub-mechanism. I mean, other sub-mechanisms are available. That's just an example. Okay, then if we're building in a hierarchical way, then we want to add our primary mechanism, which is representing the reactions of the primary fuels and their derived radicals. I say we usually keep this in detail, but actually there are some groups, particularly the group in Milan, that might want to even make simplifications of the primary mechanism to try and keep the size of the mechanism as small as possible. We'll look at reduction techniques on Friday. Then the secondary mechanism is consuming the products of the primary mechanism and forming the smaller species, which then fall into the base mechanism. So in the secondary mechanism, I would say that, well, particularly the automatic mechanism generation codes, we'll try to apply some simplifications here to stop the size of the mechanism growing. As I say, there'll be more detail about this on Friday, but a couple of examples here. The first is vertical reaction lumping. So what this is saying is if we've got reactants going through various different intermediates to form products, actually what we'll see is that actually some of those reactions are very fast, and we can apply steady state type approximations, and so we can just define a reaction that goes from reactants directly to smaller products using one reaction step without including all the intermediates. So I would call that vertical lumping. So it's lumping down the reaction chain. We might also see, well, I called it species lumping, but I would think of this as horizontal lumping. We might have parallel pathways of similar isomers from our molecule where we're going to add species concentrations together to form a lumped species. And again, we'll look at that later. So that might work unless our different isomers are going down different reaction class pathways later in this cycle. Okay, and at this stage, I guess we would look at the reaction rates compared to the overall rate of reaction and remove any reaction classes that are of low importance. Okay, so move on now to automatic reaction generation methods. So why might this be useful? Well, you know, if human expertise doesn't stay around forever, right? It has to be encoded in some way, either by passing it on to new human experts or by encoding it into a computer. And actually, you know, the human effort involved in creating a new mechanism for some of us would be very difficult. If you're Charlie Westbrook and you've been working on this for 40, 50 years of your life, you could probably do it more quickly. But actually, you know, for some of the new fuels, larger fuels, it's a huge task to generate a mechanism. Also, generating mechanisms by hand can lead to mistakes. Even typos in mechanisms can trip you up much further down the line. And you would hope anyway that a computer code that's encoded reaction classes and rate constants should make less mistakes. You know, really when we generate a mechanism, we want to do it in a systematic way. We also want to use systematic methods for estimating reaction rates based on reaction class rules and rate rules using functional groups, for example. So the idea behind automatic generation codes was to encode all of this human knowledge that has been learned and all of the data that we know about for groups in terms of thermochemistry or for rate rules for reaction classes in terms of reaction rate coefficients. Why not encode that into a computer so that we can use a method then to generate a mechanism for a new fuel? So, you know, it sounds like a great idea. If you trawl the literature for the use of automatic generation codes, you might not find an enormous number of papers, actually. I don't know if anyone's working using any of these codes. Yeah. Anyone? No. I've got a case study that I hope we'll have time to look at either today or tomorrow of our attempts to use automatic generation. So over the years, there have been several codes developed, and these are all based on kind of an expert system concept. So they're using a database of chemical principles and reaction classes, and we're using basically similar rules for reaction classes of fuels of different sizes, and then we're using information about the functional groups in our molecules to estimate the rate coefficients. And so we're trying to apply these rules in a systematic way. So the various different examples that have existed, there was one developed at CNRS in Nancy. It goes back to the 1990s called X-gas. Unfortunately, I think this is no longer being further developed. The second one that's still being actively developed actually is reaction mechanism generator developed by Bill Green's group at MIT. And that's the one that we've tried to use for a system that we're trying to model. There's reaction that was developed by Ned Bluerock. Again, I think there were some nice ideas in there, but I think that's no longer being actively developed. And then there's the MAMOX code being developed by Milan, which has been used quite substantially, maybe by other groups, but mostly by them. So even if people are not using the generator, they might be using reaction codes, like the correct code, that have been developed using these tools. So the schematic here, using X-gas as an example of the structure. So it shouldn't look too unexpected. We've got our base mechanism, and then we're adding our primary mechanism generator for our primary fuel and any radicals that come from that fuel. In X-gas, this was included at detailed level. And then when it comes to the secondary mechanism generator, there was lumping that took place to lump isomers of the secondary molecules to try and reduce the overall mechanism size. And then there was a thermochemical data generator, so based really on group additivity that I talked about earlier in the week, I can't remember what day, and then a kinetic data generator based on this concepts of reaction classes and functional groups. And in X-gas, I'm pretty sure I remember that you could select whether you wanted a low temperature mechanism or a high or a general mechanism, and you could select the level of lumping that you wanted to apply. The MAMOX code from Milan actually can produce a hierarchy of very lumped mechanisms. So I'll talk more about lumping on Friday, but I think the advantage of that is that the codes that come from that generator are much likely to have a lower number of species to solve for than the codes which use more detailed representations. Okay, I think I've already said then that X-gas allowed some mechanism tailoring on the temperature regime and the degree of lumping that you wanted to use. RNG uses a kind of generate and test algorithm. So it kind of does an on-the-fly reduction process. So it adds in a new reaction step, estimates the rate constants, and then tries to decide whether the reaction is important enough to be included in the final mechanism. And I think our experience is that can be useful, and it can also trip you up. So sometimes it decides that really important routes that you expect to be in the mechanism aren't important enough, and so it misses whole pathways, and so you've got to be a bit careful about how you use that. Reaction was set up, actually, the idea I liked about this was that it was based on fundamental chemical information from external databases rather than having its own internal database. And so the idea there is that each time you generated a mechanism, it was using the most up-to-date data, assuming that those databases were updated. Whereas X-gas, for example, was using internal databases. So there are different concepts in the different codes. So if we're looking towards new fuels, so non-fossil fuels, biofuels are one potential choice. They'll crop up in various themes throughout the rest of the week for me. But this does lead to some challenges in terms of generating codes for new fuels. So most of these automatic generation codes were developed based on alkanes. It doesn't mean to say that the concepts don't apply to other fuels. You've got to start somewhere. But obviously, biofuels look very different from alkanes. They may have double carbon bonds. They might contain, or very likely to contain, oxygen. Might contain single oxygen bonds or a double oxygen carbon oxygen bonds. And so the question is then, are we able to tune the reaction mechanism generation codes to work for these new types of fuels? Because they have different functional groups. They're going to have different bond energies compared to alkanes. There may even be different reaction classes. And so some of the data that comes from alkanes will still be relevant, but we might need to add in new data to allow us to generate these new fuel mechanisms. And we may find that as we go to more complicated oxygenated fuels, that the measurement data that we've got as our reference becomes more scarce. So that might become more obvious if I get as far as the example. Okay, so let's take an example of alcohols as a starting point. Okay, so we talked about this concept then of functional groups, and said already that if we have a tertiary carbon, it's easier to pull off a hydrogen from an alkane. If we have a secondary carbon, it's easier than it is from a primary. But now, if we look at alcohols, we've got this OH group on the end, and that will change. The electron localization and the bond energies will change. So this nice diagram, that again came from Matteo Paolucci, shows us the different bond energies for hydrogen bonds for different functional groups in a range of alcohols. So going all the way from methanol, ethanol, propanol, butanol, etc. The chain is getting longer as we go down here, obviously. Okay, so first thing to note is that actually, once we get more than 2 carbons away from the OH group, then the rest of the molecule is going to behave more like an alkane. Okay, so what you'll see here is we've got various secondary carbons, and the bond energy between the carbon and the hydrogen is the same for those 3 secondary carbons. Okay, but as we then go into the second but 1 carbon from the OH group, then we see a big change in the bond energy here between the carbon and the hydrogen. And again, for the carbon that's attached to the oxygen group here. Okay, so short chain alcohols then, we've got a strong influence of the OH group. As we move to longer chain alcohols, they become more and more alkane-like. So the influence of the OH group gets less. So it's interesting to look at then at the bond energies here. So the bond energy between the carbon and the hydrogen, where the carbon is next to the oxygen, you'll see is much lower than the bond energy here. And so what that means is that this is the favorable hydrogen that will be most likely to be abstracted by other radicals like OH, H, HO2. Yeah, there's a nice labeling system on the bottom here. So the carbon which is next to the OH group is the alpha carbon. The one next to that is beta, gamma, delta, etc. So what we can see is that for all of these molecules, short or long chain, that alpha carbon is going to be the most favorable in terms of the hydrogen abstraction. And then, actually, it's not the beta carbon which is next. It's the gamma carbon which is the next most likely to be abstracted. So you can see here bond association energy for the different functional groups here. So you can see that the lowest energies are for the alpha hydrogen. Okay, there's a slightly different labeling system here. This is called HSEC, but that's actually the gamma one. And so we can see that these are going to be the 2 most favorable hydrogen abstractions. And actually, what I want to show as we go through today is that actually it's really critical to have rate constants for hydrogen abstractions from these molecules that are site-specific. So we really do need to know where the hydrogen is being pulled off, because that's important really, because that affects the reaction path sequence that the alkyl radical that's formed then goes on to undergo, and that will affect how reactive the molecule is and how likely it is to ignite. Okay, now we're looking now at blending alcohols. Well, we already blend alcohol into gasoline, ethanol into gasoline at 10% in the UK. I'm not quite sure what's the level in the US. Yeah, so we want to know what the influence of adding that alcohol is or other alcohols or other biofuels, for example, on the ignition properties of our fuels. Well, site-specific reaction rates are pretty difficult to measure, so we might need to use other methods to get data for these site-specific rates. So I think this is probably not saying anything too different. This is just another, a more detailed example for the Butanol Isomers. Okay, so 1 or N-butanol here, straight chain, and we've got the hydrogen bond energies here. So as you can see again, this alpha hydrogen has the lowest bond energy, followed by the gamma, followed by beta, followed by delta. So this is the selectivity for abstraction by OH as an example. I mean, the different butanol isomers, you can see the bond energies do vary here because of the different structures. So the isobutanol has a branch structure, still has alpha, beta, gamma sites. Butanol only has an alpha and a beta site, actually. We've got information, we'd like to have information on the site selectivity for the abstraction of hydrogens from these different sites on the molecules. And then we need to know then what will happen to the subsequent radicals. Okay. Yeah. No, it's not trivial. It will be related to the localization of electrons because of the bonding of the carbon that's next to it. Yeah, obviously for the branch structure, we've got a different bonding structure for this carbon, which will have an influence on the bond association energy for the hydrogen from this carbon. Yeah, so basically, it's not. You have to look at the neighbouring carbons as well.
Do we see this phenomenon with other?
Oh yeah. I mean, I picked alcohols because it's the easiest one, but yeah. Yeah, I mean, I don't want to say too much more about that. I will try to bring some of these things in when I talk about the case study, actually, because it highlights some of these issues. I've got 10 minutes left, so I'll make a start. So I'm going to go on now to talk a bit more in detail about the chemistry in low temperature and high temperature situations. And really one of the things I want to do here is bring in the experimental techniques that we use across the temperature and pressure range to evaluate our mechanisms. I mean, at the end of the day, I'm going back to what I was saying on Monday. We aren't just doing this for, well, we can do this for fun, okay. We had this conversation over lunch. We can do this for fun, but actually, eventually, we do want to use the tools that we're developing to help, design new devices or to better understand the utilization of these fuels, practical situations. The point of validating the mechanisms is, to establish whether or not they are robust enough to use in a design situation. And I think I don't know how critical I want to be, but I think sometimes when we're not pushing enough to say, well, actually, we've done all this. Well, actually, let's use it now, to solve some problems. Oh, okay. I forgot I was actually going to say that on the slide. So ultimately then, we are working towards applying chemical kinetics in the design of efficient low pollution practical combustors. And I think we are starting to move into this territory now. So CFD designs of new gas turbines, potentially new engines, or at least engine modifications to use low carbon fuels, etc. And so we are starting to get to the stage where the chemistry is actually really going to help us to do that. But the problem there is that actually, two problems. One, if we bung this detailed chemistry into a 3D CFD code, it's going to be pretty expensive. And this is not really the place to validate our chemistry because we've got too many other things going on. We might have three-dimensional turbulent flows to deal with as well. And so it's not really the place to validate our chemistry. To validate our chemistry, really what we want to do is simplify the physics as far as possible. And that is why we design fundamental experiments to do that. So for ignition delay times, what we're trying to do, I suppose, is design reactors that we can model using a 0D approach. So well-mixed reactor. Okay, so we can argue about whether rapid compression machines and shock tubes are well-mixed. We'll mention that a bit later on. But in the idealized sense, they are. And so we can use them to measure ignition delay times, and we can model them using extremely detailed chemistry, fairly straightforwardly, you know, and not have to worry too much about the simulation times. Laminar burning velocities, well, you know, obviously a flame is not a well-mixed situation. And so the design of experiments there is really to try and reduce the dimensionality to a single dimension if we can. So a spherically expanding flame, you know, if it's spherically symmetrical, we can just represent it in the axial direction. Opposed to flow diffusion flames, if they're flat, we can just use a 1D model. So again, we're trying to simplify the physics as far as possible so that we can incorporate the detailed chemistry that we're trying to validate. And you know, then once we've got a model that we think we validated over wide ranges of conditions, then we might worry about how expensive it's going to be to use in a CFD code, and we might have to do something to solve that problem. So we might have to reduce the complexity or the computational cost of that model, and that will be what I'll talk about on Friday. Okay, so over the years, there's been a number of different reactors developed to limit flow complexity. And actually, one of the things I want to highlight today is that this is constantly developing field. So for a rapid compression machine, you know, measuring pressure used to be all we did. That's actually still all we do at Leeds, although we have got optical access now. But, you know, people are doing sampling, they're doing species profiling. You know, we're starting to identify compounds that we would never have dreamed of being able to measure experimentally. And so the data that we've got for validating our models is growing all the time. And we've got more and more ways to challenge the models. And that kind of throws up some interesting stuff. Okay, so I'm going to start with kind of low temperature chemistry. We tend to look at that really through facilities that look at ignition. So the rapid compression machine is the facility that we tend to apply most commonly at low temperatures, but shock tubes actually now have extended their regime of applicability towards low temperatures as well. Okay, so we're looking usually then at the auto-ignition problem at low temperatures. And actually there's practical reasons really why we want to understand the auto-ignition of various fuels. One major reason, of course, is explosion hazards if we're storing them. So as we move towards utilising new fuels, we do have to think about the safety aspects of storing them. We might have to think, you know, for adding them to vehicle fuels, what will happen in the gasoline or diesel tank when you put them into vehicles, what will happen when you're storing them at storage facilities. So explosion hazards is one reason. And also from the point of view of utilisation in engines, we might want to understand auto-ignition because in a spark ignition, for example, we don't want it. It causes engine knock, which causes damage. Or we might have new designs of engines like HCCI that are actually utilising auto-ignition properties. Okay, so one fundamental quantity that we might measure related to fuels is the minimum ignition energy. So we would expect that to happen where the reaction rate is at higher. So this is going to be the lowest energy of spark that's going to ignite the material that we've got in air. It's usually measured in joules or millijoules, actually. It's going to occur at or near stoichiometric conditions where, you know, we're also going to see highest reaction rates, highest flame temperatures, etc. So it's just it's a way of comparing the potential hazards of one fuel to another. So we measure the minimum ignition energy using a spark. So we have so this is the vessel here, a spherical vessel with a spark gap. I mean, we can actually vary that as well. But we're varying the capacitance of the charge on that spark until we get a voltage breakup. And what we're doing is testing various different energies to establish the minimum energy that will lead to ignition in the fuel mixture that we've got here. So we have to look over a range of stoichiometries and establish the minimum energy that will lead to auto-ignition of our fuel air or fuel oxygen mixture. So for most alkane fuels, we get a very similar value, actually. The stoichiometry where the minimum will occur might vary according to the chain length of the fuel, but the minimum ignition energy is around 0.2 millijoules for hydrocarbons in air. It's slightly higher in methane, which means that it's slightly more difficult to ignite methane than it is alkanes. But the really interesting thing here is when we look at hydrogen. I mean, you probably know this intuitively anyway. If we look at hydrogen, we've got an order of magnitude difference in the minimum ignition energy that it takes to ignite a hydrogen air mixture compared to methane. So, of course, that is of concern for the hydrogen economy if we want to switch fuel systems in our applications from natural gas to hydrogen. 10 times less energy, at least, is required to ignite stoichiometric hydrogen mixture. You know, hydrogen's more diffusive, so maybe it's not the end of the world. But you know, there is a concern there that it is far more ignitable. I think that might be a chance to take a break. So I'm just going to, I guess, reiterate a few remarks about auto-ignition and what causes it. I'll probably skip this slide, it's too basic. So we started out with the hydrogen-oxygen scheme and looking at the initiation, reactions, chain branching, chain propagation, chain termination. So I guess I've shown these reactions before, but one other point to note, obviously, is that to initiate the reaction, we're trying to break the bond of a stable molecule, and so we require quite a lot of heat to do that, and so these reactions are endothermic. But then once we start to form radicals, we can go through chain branching routes. Of course, the main one for the hydrogen-oxygen scheme is H plus O2 going to OH plus O, and these are slightly endothermic reactions. And then we move on to the chain propagation and termination routes, which are the reactions which are producing heat from the overall combustion. So that the hydrogen-oxygen chain branching route is quite simple. It's basically H plus O2 giving us two radicals, OH plus O. The O can go on to react with H2 to give us OH plus H. And that's competing with the main termination reaction. Well, actually, I've put this under propagation, but maybe I should have put it under termination, because the HO2 radical, under some conditions, is fairly unreactive. This is a termination reaction, but actually at high temperatures, this HO2 goes on to form hydrogen peroxide, which can break apart to give us two OHs. So this reaction here, I guess, can be classified in different ways depending on the temperature regime that we're looking at and the pressure regime that we're looking at. But our heat release comes from these final stages. So I think I've shown this already. So basically, depending on the temperature and pressure, we've got this competition between branching routes and routes that form HO2. But at very high temperatures and pressures then, this HO2 goes on to form hydrogen peroxide, and that can give us our radicals back. The only other thing I would say here, actually, is that Another competing reaction in this system is the diffusion of radicals to the reactor walls. And that's something to watch out for, I suppose, when we're modeling our systems, because sometimes reaction with the walls is actually quite important. It's going to be facility specific, but it's something to watch out for, that you've included appropriate steps in your mechanism if that is an important step. So the overall low temperature chemistry for hydrocarbon fuels is a lot more complicated, of course, than the hydrogen-oxygen. So I showed the reaction classes earlier, but this is just another way of looking at the reaction sequence. So the blue on the left here is the branching chain. Okay, so we're starting out with our parent fuel. Various different radicals can abstract to hydrogen to give us the alkyl. We've got the first oxygen addition to give us the peroxy radical. And in the low temperature branching chain then, that's isomerizing to give us a QOH. Then we've got the second oxygen addition to give us O2 QOH. I should say that actually there have been papers on third oxygen addition, but I'm not going to talk about that this week. We've got further isomerization. First of all, giving us a keto hydroperoxide plus OH, and then the keto hydroperoxide breaking down to give us this second OH, which is why we've got the branching route. And then at each stage here, we've got the competition with routes that might give us a slowing down of the reaction rate. Okay, so this route from RO2 to either olefin plus HO2 or cyclic ether plus OH can give us what we call the negative temperature coefficient regime that we see for certain fuels in combustion. Okay, so we've got routes here from the RO2 or the QOH to alkene plus HO2 or to cyclic ether plus OH. And we've got the same potential routes from the O2 QOH through isomerization or directly from that species. So we've always got this competition. And the pathways chosen will, of course, depend on stoichiometry, temperature, and pressure. This is, I guess this might be a slight aside, but it's going to be important for tomorrow, so I'm going to leave it in here for now. So the auto-ignition temperature, so we talked about the minimum ignition energy. The auto-ignition temperature is also an important quantity for fuels. So actually for diesel, the auto-ignition temperature is actually quite low, much lower than it is for petrol and gasoline. And in actual fact, hydrogen is not on this table, but it's even higher. So hydrogen, although it's got a low minimum ignition energy, it's got a high auto-ignition temperature because it hasn't got those fuel-specific low-temperature routes that we've got for the hydrocarbon fuels. Flashpoint is a different quantity. So flashpoint is the lowest temperature at which our fuel can vaporize to form an ignitable mixture. And so flashpoint is quite high for diesel. We don't really want diesel to form an ignitable mixture in our tank of our vehicle if we're still using diesel. But interestingly enough, petrol and gasoline have got gasoline, let's call it, because we're in the US, has got a flash point below 0. So gasoline is a vapor at normal temperature conditions. So why doesn't that give us problems, I guess, in terms of storing gasoline in a tank? The reason is because basically it vaporizes so quickly it forms a rich mixture in your tank, and so it's beyond the flammability limits at the rich end. And so I put this in here because I will be thinking about alternative fuels. We'll be talking about those tomorrow. And we're combustion scientists. We tend to think about the combustion properties of our fuels. So we might look at the octane number, the cetane number, and say, oh, this looks very nice, and we can use this as a blend for reducing the fossil component of our fuels. But actually, some of these practical things are going to matter. So, for example, if we if we blend something with gasoline that's got a much higher flash point, do we have the risk then of moving that back into the flammability regime? And if we're blending a fuel with diesel, are we going to reduce the flash point again into a regime which might become flammable? And so the physical properties of fuels that we want to mix with petrol or gasoline or with diesel might be very different, aside from other combustion properties that we're interested in. And in fact, there are, for diesel, there are standards which set the minimum flash point that you can have in a fuel. And so that's important when we come to think about what we might want to blend. Actually, as an aside, a COVID pandemic aside, during the early days of the pandemic, when everyone was obsessively using hand sanitizer, which were all ethanol-based, our National Health Service issued a warning that don't leave hand sanitizer in your car because it could explode and set fire to your car. So the question is, was that good advice or not? Are they right? Anyone? Okay. Well, okay, you're right, but that wasn't necessarily the answer I was looking for. The problem was that basically they basically confused the flash point with the auto-ignition temperature. So ethanol might vaporize, but unless it, got in contact with a lit cigarette, it was not going to auto-ignite because the auto-ignition temperature is pretty high. So it would have had to have come into contact with a spark or some kind of burning material. Anyway, it was just an interesting aside on how these two things quite often get confused. So I'm just showing here the auto-ignition temperature of various different fuels. So we're looking along different lengths of carbon chain. And actually, for larger hydrocarbons, they all tend to a very similar auto-ignition temperature of around 200 degrees for liquid hydrocarbons. So the auto-ignition temperature for methane, for natural gas, is much higher, and for hydrogen, even higher again. Okay, so under normal atmospheric conditions, none of these fuels should auto-ignite. They'd have to come into contact with either a hot surface or a spark or something like that. Okay, so that's more the kind of data that we would look for in terms of hazard applications, but we will have to think about safety aspects of alternative fuels as well as their combustion properties. And so it is important to think about these things. From the point of view of utilizing fuels in combustion devices, in terms of ignition, then of course the ignition delay time is another critical parameter. Very specifically important, of course, in engine applications, but also it's a test of our chemical mechanisms, I guess, and their ability to predict ignition behavior. We can measure ignition delay times in different devices. Usually at low temperatures, we're using a rapid compression machine, but also we can get ignition delay time data from shock tubes, of course. And by combining the data from those two types of facilities, we should be able to cover the whole temperature range. There's slightly different ways of expressing the ignition delay time. This is from data from a rapid compression machine. So ours at Leeds is a single piston rapid compression machine, and the ignition delay time is defined as the time from the end of compression to the maximum gradient in terms of the pressure rise. So on this plot here, we've got the pressure trace in blue, and then we've got the pressure rise rate in red. Okay, so the end of compression will be at the end of this first peak here, and then the ignition delay will be the time from the end of compression to this peak in the pressure rise rate here. There are other ways of measuring ignition delay, so in shock tubes maybe, OH emission might be used, but they should really be compatible to within quite small errors. So this diagram is just showing, I guess, how the data might come together to give us an ignition delay time plot. So this is for hydrogen-oxygen argon system at lean conditions. But actually, I've just showed it here really just to show you how we normally present this data. I mean, you may have seen many of these plots before, I don't know. But normally, we present the ignition delay time on a log scale, and we're plotting that against some function of the inverse of temperature. So, I mean, this is usually 1,000 over K, 1,000 over T, sorry, is the way in which we do this. So if we have a straight line for our ignition delay times plotted on a log scale against some function of 1 over T, that would represent Arrhenius type behavior for the overall reaction. Okay. And we do see that for some fuels. We don't see that for hydrogen-oxygen systems in this case. Okay, so you can see here that there is non-Arrhenius behavior for this system. Well, okay, I've been over the hydrogen-oxygen chemistry probably a number of times now, so won't dwell on that. But it's just to show you really that we have different facilities that will help us to gather ignition delay times at different temperature regimes. And of course, they do have different pressure regimes as well, because we need this data over a range of temperatures and pressures. Okay, if we look at a similar plot for certain hydrocarbons, so this is N-pentane oxidation in air at 20 atmospheres, then again we see quite non-Arrhenius behavior. So plotting on a log scale against 10,000 over T, and we actually see change in slope in this diagram. Okay, so if we start out at low temperatures, as we increase the temperature, the reactivity increases, and so the ignition delay time shortens. But then we hit this region called the negative temperature coefficient regime, where we increase the temperature, but the ignition delay time actually lengthens. So what we're seeing is a reduction in reactivity as the temperature is increasing. Okay, and then as we get to higher temperatures again, then increasing the temperature rapidly shortens the ignition delay time. Of course, at high temperatures, the ignition delay time is very short. So this negative temperature coefficient region here is common for some hydrocarbon fuels. This non-Arrhenius behavior, and actually one of the things I'll show you is that models quite often struggle to get this right, to represent the depth of this NTC region. Not all fuels show an NTC. So this is a plot of ignition delay times for ethanol air mixtures from a paper by Sarathi et al. You can see here it's not quite Arrhenius for some of these conditions, but this is closer to being Arrhenius behavior for this short chain alcohol. Okay, so at 40 bar in the RCM, actually, we do see almost Arrhenius behavior, but there is a tail off in terms of the decrease in reactivity as we go to lower temperatures at 10 bar and at 50 bar. Would perhaps apply some caution here. It is probably likely that as we go to longer and longer ignition delay times, that facility effects from the RCM will start to play a role. And so I think we would expect the error bars on the long ignition delay times to be larger than in the intermediate temperature regime, for example. Okay, so several of the smaller low carbon number alcohol fuel types do give us more Arrhenius type behavior when we look at the ignition delays on the log scale with respect to 1 over T. But as I showed earlier when we were looking at the molecule structures, as the chain length gets longer, the alcohols are going to start to behave more like alkanes. And so for the very long alcohols, we might be interested to know whether that they actually then redevelop an NTC region. I think basically this is not that different from things I've already said. Has everyone got the hang of low temperature branching routes now? Shall I move on from this plot? There it is again. Got plenty of material to help you understand low temperature branching routes. It's interesting to think about what causes the NTC. And the key to reactivity is actually the fate of the alkyl peroxy radicals, the RO2 radicals, in that low temperature pathway route. So they had a number of different potential reactions that they could undergo. When we have chain branching, then they're going to isomerize to the hydroperoxy alkyl radical, or QOH. But the reaction from alkyl to RO2 is reversible. And actually, at lower temperatures, RO2 can reform the original alkyl R plus O2, or it can dissociate to produce an alkene plus HO2. And this formation of HO2, and then what happens to the HO2, is actually the key to the NTC region. And actually, this has some commonality with the hydrogen mechanism. So it's lower in reactivity than OH, and at intermediate temperatures, it goes on to form hydrogen peroxide. Hydrogen peroxide is fairly stable until we get to higher temperatures. So in the intermediate temperature regime, forming HO2 and then forming hydrogen peroxide is actually kind of, can be, I guess, seen as a chain termination routine, or at least a reactivity slowing pathway. But actually, as we get to high temperatures, then H2O2 can decompose to give us two OH radicals back, and then the reactivity starts to increase again. Okay, so in that intermediate region of the NTC regime, we're going to see the importance of the reverse reaction from RO2 to the alkyl and its dissociation to an alkene plus HO2, and we're likely to see the importance of HO2 chemistry in that intermediate temperatures regime. One of the things we've been working on at Leeds is actually extracting heat release information from our pressure traces from rapid compression machine experiments, and looking to see what reactions are important in terms of dominating the chemistry in the different regimes. It's early days with this work yet, actually, and one of the first things to note here is that let me go through what we're doing. So in this set of experiments, we were looking at a 5-component surrogate to a gasoline compared to gasoline in the RCM, and then we were blending various proportions of isobutanol with that gasoline to see what the influence was on the ignition behavior. And then we tried to simulate that with a blended mechanism that was I guess now the older version of the Lawrence-Livermore gasoline surrogate mechanism, coupled with the butanol mechanism from Sarafi. Okay, and actually, we get pretty good representation of the ignition delay behavior. But I wanted to know really whether or not we were able to simulate the heat release. The model here are the dotted lines, and the solid lines well, I'll talk about how we do this a bit later on, but basically they are derived from the experimental pressure traces. So, there's some noise in the experimental data for sure. But one of the things that we see is that we see 3 stages actually of heat release. So we see 2 low temperature heat release stages before we see the main ignition event. And that is more pronounced for the gasoline surrogate. But then as we add more butanol, into our mixture, then that low temperature heat release is actually suppressed. And what that means is that, actually the butanol is suppressing this low temperature branching routes. So the first heat release stage is dominated, as expected, by the low temperature chemistry, this isomerization of RO2, the second oxygen addition, formation of keto hydroperoxide, etc. The second stage is dominated by the reactions of HO2. So the reaction of HO2 plus the hydrocarbon, so hydrogen abstraction by HO2, and also the hydrogen peroxide chemistry. And then the third stage heat release is dominated by, I guess, the kind of reactions we would normally see in flame simulations at high temperature, so CO plus OH and OH plus HO2. Okay, so we've got 3 different stages of heat release during our ignition, and each stage is dominated by a different part of the chemical pathways. But the reality is that the chemical mechanism is actually over-predicting this low temperature heat release compared to the experimentally derived data. So there's definitely something awry there in how we're predicting heat release from that mechanism. And that is, I guess, maybe likely to relate to the thermochemistry, but I'll come back to that later. Okay, so we're adding, we've done some work on isobutanol and N-butanol in terms of its influence blending with gasolines and surrogates. And we established in the last plot that isobutanol is suppressing the low temperature heat release. And this is generally true for short chain alcohols, particularly for ethanol. So actually, one of, I suppose, the advantages of blending bioethanol into gasoline is that it is suppressing low temperature heat release and potentially suppressing NOx. Okay, so it's an octane enhancer, which in spark ignition engines is useful. So in the previous slide then, I suggested that the H abstraction from the alpha site is dominant for alcohols due to the lower energy barrier. And what happens then is that favors reaction sequences that lead to a carbonyl plus HO2 pathways over the chain branching pathways that would lead to QOH and the second oxygen addition. So what that means is that when we start to blend butanol into the gasoline or the gasoline surrogate, then we are slowing down the low temperature heat release and slowing down the low temperature chemistry. Okay, so this diagram here, if I put the reference, it comes from the Sarathi paper as far as, yeah. Basically, if we abstract from this alpha site here, then we form our RO2 radical, which goes on to form HO2, and this is a termination route. We will see, of course, some abstraction from the other sites. So the second most favoured site was the gamma site here, and this is the site that actually leads to the normal chain branching routes that we understand from alkane chemistry. Okay, so both for isobutanol and for N-butanol, we see the suppression of low temperature chemistry for most of the temperature regime when we add that to the alcohols. Okay, so I guess this is a similar information, but just hammer home the point. The site of the initial abstraction is going to determine whether the branching or the termination routes are going to dominate. This is a bit of a complicated, messy plot, actually. But this is basically showing the effect of blending various different levels of N-butanol, in this case, into gasoline and a gasoline surrogate, the impact that has on the ignition delay times over a broad range of temperatures that we can cover in our RCM. So there was two aspects of this work. The experiments were done with both gasoline and with a surrogate gasoline based on a toluene reference fuel. So that's toluene plus N-heptane plus isooctane blends. Okay, so that's a 3-component surrogate. that we're using to attempt to mimic the gasoline. Because obviously, in terms of numerical methods, we don't have a chemical mechanism for gasoline because it obviously contains a very large number of compounds. And so if we want to model gasoline and its blends numerically, then we have to come up with surrogate mechanisms to represent the gasoline chemistry. So at this stage, we were only using 3 components, and later we actually moved up to 5 components, which did give a slightly better agreement. But so the gasoline here on the right are the purple stars. So you can see, in terms of the ignition delays for the gasoline, we've got this weak NTC. And actually, we did manage to reproduce that with our toluene reference fuel. The behavior is very similar. And so under these circumstances, this is not the model, this is experimental data. The surrogate that we chose was a reasonable representation of the gasoline. The N-butanol here is the dark orange line. So it's not quite Arrhenius, the behavior. We sort of see this flattening a little bit in the intermediate temperature regime here. And what's interesting about this is actually for both the gasoline and the surrogate, actually the N-butanol crosses the gasoline curve. So at temperatures below about 800 Kelvin, then the N-butanol has significantly longer ignition delay times than the gasoline. So we're seeing that suppression of the low temperature chemistry. But actually, above 800, the N-butanol is actually giving shorter ignition delay times. So it's not providing that octane boosting effect there. That isn't the kind of quirk of using a surrogate, because we also saw the same in the gasoline data. So that's interesting because it means what will happen in an engine in terms of whether N-butanol is octane enhancing or not, or suppressing NOx, will depend on the temperature conditions in the engine. Okay, so it's not as effective suppressing NOx as ethanol, but actually it has other better properties than ethanol in other ways. I might mention that tomorrow, actually. But and then for the blends in between, we do see again some crossover between them. It's only really the low butanol blends that show the NTC region. So we still see the NTC at 10% butanol. We still see a little bit of an NTC in the gasoline data for 20%. When we get up to 40%, the NTC has disappeared. And actually at 40%, we do see longer ignition delay times across the whole regime. But then when we increase the butanol further, we see this shortening. Okay, so there's some non-linearity in the effects going on here. When we look at different blend ratios. And I think the reason is because we've got this interaction of the adding of N-butanol is interacting with the chemistry that's involved in the NTC region for the gasoline itself. So do a sensitivity analysis. Well, we did lots of sensitivity analysis for the blends and things like this, but this is just basically showing the data for the N-butanol. So just to see really whether it actually corresponds to what we might expect from our understanding of the functional groups in the molecules. And actually, the higher sensitivity that leads to a lowering of the reactivity as we increase the rate constant is this hydrogen abstraction BioH from the alpha site. So that's as we expect. And then the second most sensitive reaction is then the oxygen addition here, but actually directly forming HO2. Okay, so that's again as we expect. The third most important reaction is opposite in sign. So what that suggests is if we increase this reaction rate, it will lead to a higher reactivity And this, as we might expect, is the abstraction from the gamma site of N-butanol. Okay, so those are the three main sensitivities that are dominating, and they actually, well, pleasingly, I suppose, they correspond to what we might have expected. I will be talking more about global sensitivity analysis on Friday, but just to explain this plot, what we did was a kind of pseudo Monte Carlo type sample of uncertainties from within our combined mechanism, and did a sensitivity analysis based on that sample. So what this is showing is the contribution to the overall variance in the prediction of the ignition delay times that comes from uncertainties in each of these reactions. Will I explain that again? So this is on a scale of 0 to 1, but let's say it was on a scale of 10% to 100%. Well, if we take the low temperature here, what this is saying is that this first reaction, which is hydrogen abstraction by OH from the alpha site, is contributing about 25% of the predicted uncertainty in the ignition delay times. Okay. So it's a little, I will explain all this fully on Friday, but basically this is different from just doing a straightforward local sensitivity analysis. I mean, straightforward local sensitivity analysis will tell you what the important reactions are, but they won't tell you how much of the variance in your predictions are coming from uncertainties in that reaction. So that's what we're trying to establish here. Looking at the lowest temperature again, what's this? About 15% of the uncertainty is coming from the abstraction from the gamma site, probably about 20% from the oxygen addition to that alpha alkyl radical, and forming RO2, and then another maybe 20% forming aldehyde plus HO2. And what that shows is really, which is useful to know, let me include one more, which is the abstraction by HO2, which becomes actually more important at the intermediate temperatures, as we might expect. Okay, so we always expect to see HO2 being important, not at low temperatures, but at the intermediate temperatures more so. So what this says is we've got these 5 reactions at the bottom are contributing up to 80, 90, I mean, at these temperatures, almost 100% of the output uncertainty. So what it suggests is that if we can constrain much better the uncertainties in these 5 reactions, then we can get really high fidelity predictions. And actually, there's hundreds of reactions in the scheme, but most of the output uncertainty is driven by these 5 rate constants. So that's sort of useful, and that's why sensitivity analysis is useful, because it helps us to sort of hone in on key parameters that we need to do more work on to get better estimates. That makes sense. It might, hopefully by Friday, this technique will make more sense. I've written myself a note to remind myself to say something here. So for the most part, what you'll see is that the ignition delay times are driven by fuel-specific chemistry, right? So, but at high temperatures, this decomposition of hydrogen peroxide to 2OHs does creep in, which is expected, I guess, from the theory. So for the most part, it's fuel-specific, but we do have this one reaction from the base scheme that becomes important at high temperatures. Okay. I had animation. Okay, so at low temperatures, just to reiterate then, the initial abstractions by OH are going to dominate. At high temperatures, the HO, or in intermediate and high temperatures, the HO2 and hydrogen peroxide chemistry will increase in importance. Ooh, I've written myself a note here that I've got a typo. This should be gamma. I think it might say beta in the notes, so if you've got your notes open in a pen, it'd be good to correct that, if you don't mind. So this is again an output from a sort of Monte Carlo type uncertainty analysis. So in that type of analysis, what we're doing is we're setting uncertainty limits on certain parameters in the model, and then we're doing a kind of quasi-random sample of, in this case, pre-exponential factors from within those uncertainty limits, and we're simulating the ignition delay time across maybe, I don't know, I can't remember what the sample size was, but let's say it was something like the order of 1,000. Okay, so each cross here is a simulated ignition delay time from that quasi-random sample. Okay, so we can plot the log of the ignition delay time against the uncertainty in our A factor for a particular reaction. This has just been normalized to its scale between 0 and 1. It's a fairly scattered plot, right? But actually, we've got methods that we can pull out the sensitivity to this particular parameter, which is the straight line here. So what you can see is that on a log scale, the log of the ignition delay has really a linear relationship with the A factor for this particular reaction, which is the abstraction from the alpha site. That makes sense. Okay, so as we increase the rate of this abstraction from the alpha site, of course, the ignition delay gets longer because we're reducing the reactivity. On the right, we've got the abstraction from the gamma site. We expect an opposite sign here because abstraction from the gamma site is going to lead to our chain branching pathways. So increasing the A factor for this reaction is going to lead to shorter ignition delay times. Okay, so using global sensitivity analysis methods, we can pull out this functional relationship for these two abstraction rates. What's potentially, I guess, more interesting is looking at the sensitivity to the scale branching ratio for abstraction from the alpha and gamma sites. And here the relationship looks a bit more obvious. The sensitivity index for this ratio is 0.7. So what that says is that getting this ratio, the uncertainty in this ratio is leading to 70% of the uncertainty in the predicted ignition delay time. So it's the dominant factor that affects our ability to predict the ignition delays. But what is even, I guess, more interesting is that the sensitivity index for the total rate of butanol plus OH is really small. It's less than 10%. So what this tells us is that predicting ignition delays is really not that sensitive to the overall reaction rate of OH plus the fuel. It's actually far more sensitive to the relative branching ratios of the main abstractions from the alpha and the gamma site. So to get good predictions of our ignition delays, we really do need site-specific reaction rates for those abstractions. And actually, if you're interested, there is a poster on site-specific abstraction rates in the poster room. Yeah. I'm supposed to repeat the question, but I actually didn't hear it. Can you? Okay, so the question is, how costly are these global sensitivity analysis methods? Yeah, they're costly. But don't forget, basically, we're using a 0D code here, and so we can actually afford them. I'll talk about this more on Friday, but basically what we tend to do is do a local sensitivity analysis first and maybe pick out 30, 40 reactions that rank highly in terms of local sensitivities, and then we sample from that, dimensional hyperspace for the global sensitivity analysis. But it's actually maybe not as expensive as you think, because For ignition delay times, we don't have a simple way of calculating sensitivities through Chemkin anyway. We have to do it using brute force. So actually running through each of the reactions using a brute force method where we're modifying each one in turn is also pretty expensive. And actually the global sample is probably smaller than that. So I'll talk more about this on Friday, but the sample size goes up as 2 to the power n. So this is probably 1,064. I can't remember exactly what we did here. So it's basically 1,064 simulations using either Chemkin or Cantera of, constant, variable volume, actually, RCM. So I don't know, it's probably no more than a day, depending on how many processes you've got. I mean, obviously, for flame calculation, it's going to be more expensive, and to do it for a 3D CFD calculation, it's going to be very expensive. Does anyone remember what time I was supposed to finish? 15:15. Sorry? 15:15, is it? Okay, so why is any of this important? Well, if we are still going to continue to use CI engines for the future, then we obviously need to be thinking about blending in larger and larger volumes of non-fossil fuels or renewable fuels in some way. And so we need to know whether or not the fuels are going to be compatible with our engines. So for spark ignition engines, what we're trying to do is to develop fuel blends that will either not make the NOx situation any worse or might actually enhance our NOx suppression. So I suppose in the simple way, we're looking for fuels with a higher or equivalent octane number to the gasoline we're using. Or basically, we're looking for fuels that have longer ignition delay times to avoid NOx. So I'm sure you all know what NOx is, but basically in a spark ignition engine, obviously we're trying to control the ignition through the spark. What we don't want to happen is auto ignition away from the expected flame front, because that can lead to pressure fluctuations, which can lead to that pinging, knocking sound that is associated with NOx, and it can lead to engine damage, which is shown on the piston head here. With diesel, really we're looking for auto ignition because we get ignition through the compression of the fuel up to compression ratios of about 20. So in the normal diesel engine, we get compression and then we're spraying the fuel into the cylinder, and that's fine. And diesel engines work very effectively, but unfortunately, because this is not a well-mixed situation, we can end up with rich zones in the diesel engine, which leads to formation of soot, for example. So HDCI engines, homogeneous charge compression ignition engines, is attempting, I suppose, to combine the useful things about both of those two engine strategies. So in an HDCI engine, the fuel is homogeneously mixed with a very high proportion of air to fuel, so we get a lean mixture, and that is then compressed. And then we're using auto-ignition to ignite the fuel on the compression stroke. So in that sense, we're using compression to get ignition, which is much like a diesel engine. But unlike a diesel engine, we need a homogeneous mixture. So I guess the question is, why has we do see some vehicles on the market that are running HDCI-like type engines. But the problem with HDCI is because we're actually using auto-ignition to control our process, then it's quite hard to control that through the fuel controls. So different fuel components within the mixture could be used to control the ignition timing, but it's very, very sensitive to the fuel mixtures. So I mean, on the upside, I suppose, understanding the ignition delay over a range of temperatures and pressures could help us better design these types of devices. Yeah, maybe I should have chosen a slightly more fancy-looking RCM to put a picture of here. The Leeds RCM is still going. It's been going quite a long time now. We have made improvements to it, honestly. So this is the Leeds RCM. It's actually based in Mechenge at Leeds. It's actually, RCMs can be single or dual piston machines. Ours is a single piston machine. It's designed, I suppose, to mimic the compression stroke that we see in engines. So what we want is a rapid compression if we can, to avoid any chemistry occurring during compression. And then we're measuring the pressure rise using pressure transducers to capture that auto-ignition. So just to reiterate, that the ignition delay time is the time from the end of compression to the peak in the pressure rise rate. We're using laser-based piston location measurements. At the moment, we do have optical access to the RCM. We haven't really used it for too much just yet. This is in progress work. Some newer designs of RCM are able to perform rapid sampling, and that's really useful because, as well as the ignition delay time, we might actually get species profiles through the ignition, or using gas chromatography, we might also get really detailed species profiles of the products. So, as I said at the beginning, ideally, we're trying to model these things using zero-dimensional models in terms of the space dimensions. But, I mean, there have been some CFD studies of RCMs. Some of this was done at Leeds, and some by Lee and Hochreb, showing that actually we would like to think that the RCM is well mixed, but in reality that isn't really exactly true. So for a normal RCM with a flat piston, what we can see is this vortex rolling up from the colder boundary layer in the chamber. And of course that's going to lead to inhomogeneities in our reaction cell, which makes the data quite difficult to use from a model validation perspective. One of the solutions to that was to redesign the piston head with this crevice, which is supposed to capture the boundary layer and stop that boundary layer air mixing with the core of the reaction chamber, which we want to assume is adiabatic. I mean, when we started collaborating with Mechenge, doing experiments in the Leeds RCM, they were actually using flat pistons. They'd done some CFD actually that suggested that the crevice can actually re-release boundary layer air into the chamber, and so they were a bit nervous about crevicing the pistons, in fact. But when we were looking at some lower reactivity fuels that had quite long ignition delays at low temperatures, we found some pre-ignition problems and other things that were causing difficulties for us. And so we redesigned the piston head to crevice it, and actually that made those problems go away. So we have crevice piston heads now in the Leeds RCM. Just to come on to some more practical issues around how we define fuels. So historically, we've kind of defined fuels for spark ignitions according to their octane number. So basically, two values for the octane number: the research octane number and the motor octane number, which is supposed to give us an idea of how much NOx suppression capability our fuel has. Where do those octane numbers come from? Well, they come from basically ignition delay measurements for primary reference fuels. So a primary reference fuel is basically isooctane plus N-heptane. So isooctane is the least reactive of these, so it has the longest ignition delays through the whole of the temperature regime, and is classified as having a RON of 100. N-heptane is the more reactive of the alkane fuels and is classified as having a RON of 0. And so we can compare ignition delay times for other fuels to the equivalent ignition delay time from whatever mixture we've got of our isooctane and N-heptane. And that will give us the octane number for the fuel. Okay, so here we've got fuels which are 90% isooctane, so that's RON of 90, 80%, 60%, 0, etc. So this is where the kind of use of primary reference fuels came in, and it's used to help define the octane numbers for other fuels. After the break, we'll go a bit further into whether this is a good idea. So actually, let's, if it's nearly 1:15, let's take a break now. And after the break, we'll talk about whether octane number is the right approach. I don't know how much I want to dwell on this, to be honest. So we have two types of octane number that traditionally we've used to categorize fuels. The research octane number, which is obtained in a test engine at fairly low speed, milder driving conditions, so that corresponds to slightly lower temperatures as well. And then we've got the motor octane number, which is determined at a higher RPM, 900 RPM, compared to 600 for the RON. And that is supposed to give us octane numbers across the different ranges that we might have seen in engines. But actually, engines have changed in their design, and there's a lot of people, particularly Derek Bradley at Leeds, actually, are not very happy with continuing to just use octane numbers as a method of categorizing fuels. And the reality is that basically they're not that easily extrapolated on their own to modern downside boosted engines. I'll come back to that a bit later. The cetane number we use for diesel fuels is related to the inverse of the octane number. That comes from N-cetane, which has a defined cetane number of 100, so that readily ignites under compression. And so we're comparing other fuels relative to N-cetane. So, as I say, we've got regulations on cetane number, or maybe I haven't said that already, but in Europe, the cetane number has to be 51, and in the US, it has to be 40. So, in fact, the US is slightly more relaxed in terms of cetane numbers. But I will be coming back to this tomorrow, because as we start to try to develop renewable fuels that we can blend, then we have to potentially have to meet these standards if we're trying to develop drop-in fuels. So by drop-in fuel, I suppose what I mean is a fuel that can be blended under the current regulations, current engine designs, and that can be utilized. I mean, so ethanol has been a drop-in fuel. We've gone from 5 to 10% in Europe and the UK recently. So we're not changing fuel delivery systems, we're not changing engines, but actually beyond 10%, perhaps we would struggle with ethanol. So, you know, I mean, we can develop fuels that require engine redesigns, but if we want to continue to keep increasing the renewable content of our fuels, then ideally we want fuels that can be blended without massive changes. Okay, so we want to use, I mean, I favour really, I suppose, rather than using octane numbers, is actually looking at the whole ignition delay profile over different temperatures and pressures and stoichiometries. And actually, and this is one area, I suppose, where if we were able to develop a robust model, so a well-validated model, then we could use the model in place of doing what are quite time-consuming experiments. So the idea, I suppose, would be that we would do some experiments with which to validate the model, and then we can use the model to look at different blends under different conditions and to predict the ignition delay properties. So how do we model the RCM? Well, we try to do this in as simple a way as possible, and it it is actually feasible to criticise this because, as I said, the RCM is not completely a well-mixed reaction chamber. But what we do is we adopt the adiabatic core hypothesis. So this is assuming basically that a boundary layer exists along the wall of the combustion chamber, and there's heat loss to the, from this boundary layer to the walls, but in the core of the reaction chamber, we're not losing heat, so the process is adiabatic. So we've got our compression in the machine, and then in order to present the data, we need to actually determine what the temperature is in the chamber at the end of compression. So when we're presenting data on ignition delays against the inverse of temperature, that's not the starting temperature of our fuel, it's the temperature at the end of compression. Okay, and this is a function of the compression pressure relative to the initial pressure and the temperature-dependent ratio of specific heats for the mixture. Okay, so of course that value for gamma is going to depend on the thermodynamic properties of our fuel. So I mean, actually, we use a readily available code like Cantera can easily help calculate these for you. The simplest modelling approach for an RCM is to treat it as a constant volume, well-mixed reactor. But actually, in reality, we do see some heat losses occurring during compression. I might just flip to the next slide and then flip back. So the plot on the right from Sung and Curran is showing the pressure for non-reactive mixtures for different bath gases after the compression stroke. And you can see that actually, depending on the temperature in the bath gas, we will see a loss of pressure in the chamber over time. Okay, so I can't quite read that actually. What's on the right? So nitrogen has the lower heat losses compared to argon in this case. So we have to account for that actually in our model really, because actually as a result of that the volume is going to change. And so what we would do for all our experiments is, as well as doing the reactive cases where we might be using air or oxygen, for example, we're also carrying out non-reactive cases where we're replacing the oxygen by a non-reactive mixture, which is usually nitrogen. And then we're looking at the volume profile for the non-reactive case and using that in that volume profile in our simulations. So when you're presenting RCM data, you really do need to present these non-reactive cases as well, so that anyone that's using the data can incorporate those into their models to compare against your data. I mean, the reality is that the differences aren't huge, particularly at high temperatures. The differences are quite small, but you do see some deviation between the constant volume simulations here and the variable volume simulations. So this is for 10% butanol surrogate gasoline mixture. So we do see some deviation at the longer ignition delay times. Okay, so that's just a note to anyone who's doing RCM measurements to provide not only the reactive data, but also the non-reactive volume profiles. Okay, and so we can use then our measurements to assess how well our models are doing. And so, as I say, as part of our work, we're looking at blending alternative fuels into gasoline, but we wanted to check out first, our ability to simulate the gasoline that we're blending with. In this second part of our work, we actually developed a 5-component surrogate blend. So this would be toluene, isooctane and heptane, 1-hexene and ethanol. And actually, experimentally then, we first of all compared experimentally our gasoline to the 5-component surrogate. So the gasoline is the... I've lost the... Can you all see that? Because I know it's gone into night mode, hasn't it? Which is why it's not very clear, but I don't know, I'll have to... Is it all right as it is, or shall I? Yeah. So the blue is the gasoline, and the, whatever colour that is, dark pink, is the experimental data from the surrogate mixture. And as you can see, it's a pretty good representation of the gasoline experimentally. It's got a slightly weaker NTC than the gasoline, but it's fairly close. But actually then when we simulate that with the earlier version of the Lawrence-Livermore gasoline surrogate mechanism, we really cannot reproduce that NTC, and that's problematic from the point of view of then wanting to understand what happens when we blend. And there is a more recent version of the Lawrence-Livermore scheme, which is slightly better, but still doesn't give us this full NTC profile. So I'll say perhaps a bit more about that later. Okay, so for the most part, for RCMs, we are simulating ignition delay times. But the sensitivity analysis that I showed earlier sort of was suggesting that, it's not testing a huge proportion of our mechanism. There was 5 reactions from the scheme that were determining, the predictability of the ignition delay times. So really, the ignition delay times are sensitive to this, ratio of branching to termination routes. So the question is that all we want, or do we want our mechanism to be more generally applicable? And if we want that, then maybe we need to include new targets for our mechanism to test it further. So I guess one of the points I want for you to take home today is that actually, the more robust mechanisms will be developed by presenting them with the wider range of targets that we've got experimentally. Ideally then, on top of things like ignition delay times, flame speeds, we might also want species measurements that can allow us to test the intermediate parts of our schemes. Jet stirred reactors can be used to do that. Very straightforward to model. I think I showed you the equations on Monday. They tend to be operated at low pressures. There are some high pressure jet stirred reactors, but most of the data is at lower pressures. And we probably need some species validation at higher pressures. And that's coming now from sampling from shock tubes and from rapid compression machines. So we're not doing this at Leeds, but other groups are now sampling from the RCM. And the important part here is really to make sure that, because this is an invasive technique, we're grabbing a sample, that we don't have reactions continuing in our sample line, so that what we're actually investigating is what was happening in the reaction chamber. So the way in which to do this is to quench the entire reactive mixture through rapidly puncturing a diaphragm into the chamber, or using fast-acting sampling valves to do this. And then we can send our mixture to gas chromatography mass spec or FID methods and get information on the species profiles throughout the ignition. So there's a very nice review by Goldsborough et al. On this extension of RCMs to give us species profiling. So I just put one example in here for propane oxidation. So this gives us then basically a broader set of targets to compare our model with. And actually, in this case, it's highlighting some discrepancies between the model and the experiments. Propene, for example, alkenes are over-predicted. Just let me check. Or I guess the solid lines. Yeah, over-predicted by the model. And so, we might be able to predict the ignition delay times quite nicely, but we're not actually able to predict all of the intermediate species particularly well. So there's an example here for a biofuel. And again, the authors are suggesting that while ignition delay time predictions are in agreement with the experimental data, including speciation is highlighting some uncertainties in the reaction chemistry, particularly of unsaturated esters and small hydrocarbon intermediates. So we've got some aldehydes here where modifications of the model had to be made in order to reproduce that data. Okay, so this is useful because we're increasing the range of targets that we're able to evaluate our mechanisms against. Okay, another example here for isobutanol. So again, the mechanism is predicting fairly well the ignition delay times, but in this case, it's over-predicting ethane by, a factor of about 10. So that's quite a gross over-prediction of ethane here, and under-predicting isobutene by a factor of 2. So we can do a sensitivity analysis of our model and see which reactions are likely to be important in these predictions, and then go back and try to obtain higher level data for these. So I guess if there's no experimental kinetic data to improve the rate, theory might be used to try and get a better estimate of these rates. So we could restart the conversation about whether the rates should be tuned to fit the experimental data or not. I mean, ideally, you want to go back to fundamental source of the data rather than, modifying things by a factor of 2 or 5 or whatever. But, these things do happen. So I showed you a bit earlier on some heat release rate analysis that we carried out at Leeds. Actually, that was based on a technique that was developed by Scott Goldsborough at Argonne for looking at heat release analysis from pressure traces for the RCM. So I guess the most important equation here is how we predict the heat release rate. And again, it's really important here to have done the non-reactive case experiments because we need to be able to represent heat losses in this equation. Okay, so the heat release rate is a function of, again, the ratio of specific heats, which we have to calculate through the ignition. It's related to the pressure minus the pressure for the non-reactive cases, and also related to the pressure changes, the pressure gradients, the gradients in volume, and the rate of change of the ratio of specific heats. So we can extract this information from the pressure traces from the RCM if we've got the non-reactive traces as well. But it does require some modelling. We have to use Cantera to give us this ratio of specific heats. So I would say it's not an experimental measurement directly. It's a quantity that's derived from experiments. Makes sense? And what we found was that actually when we test our mechanism's ability to predict the heat release rate, again, we're not doing too well, I guess. So this is our 5-component surrogate. The solid lines are the heat release rates that are determined from the experimental pressure traces, and the dotted lines are our simulations. So we're over-predicting these first 2 stages of heat release from the model. And the same is true for the blends when we start to add isobutanol. So we know intuitively that heat release rates are going to be strongly affected by the thermodynamic data in the model. And so in this study, we did a kind of sensitivity analysis to the heats of formation for all of the species in the model. So it was a fairly simplistic approach because we varied everything by the same amount, which is 5 kilojoules per mole. So for some species, that's ridiculous because for the hydrogen species, we know the rate, we know the heat release. We know the heats of formation much better than that. But it was just a broad brush approach to see if any species kind of popped out as being a bit weird, I suppose. So what we're looking at is the percentage change in the predicted low temperature heat release peak that occurs due to a 5 kilojoule per mole change in the enthalpy of formation for each of our species. Okay, there's a large number of species in the mechanism, and most of them don't have any impact on the predicted heat release rate. Okay, so we've got 900, up to nearly 900 species. Most of them lie on this flat line. But we've got a few strange species that pop out as being quite influential, and I'll probably forget the names, so I'll have a look. So these are basically species that come from the toluene part of our surrogate mechanism, and I'm not sure that we would expect them to be so influential. So it suggests that there's something a bit strange going on with the thermodynamic data for these species. So benzyl alcohol is the one that's reproduced here, and let me just check what yeah, the benzyl oxy radical is the one. So it's a peroxy radical that comes from toluene is here. So it's not that surprising that these species would have high uncertainties, because if you remember, I said earlier in the week that where we've got oxygen bonds that we don't have perhaps as much information in terms of group additivity type relationships. And now, of course, we've also got a ring here, which also gives us problems with group additivity. So estimates of the thermodynamic data for these species are likely to be fairly uncertain. And it may well be that that's giving us a quirk in the mechanism. It's affecting the heat release rate. And whether that influences our prediction of the NTC, we haven't actually tested that yet. Actually, well, it was their technique that we borrowed anyway, but actually the group at Argonne also found something similar in their comparisons of predicted and experimentally derived heat release rates for blends with ethanol. So they were looking at two different surrogate gasoline blends and looking at different volume percentages of ethanol from none up to 30%. And again, they were seeing over predictions of the low temperature heat release. And actually, the mechanism wasn't able to really distinguish between the two surrogate designs that they tested experimentally in the RCM. So I suppose at least you could say that's consistent between the two studies. So there's two different RCMs. We were looking at isobutanol, they were looking at ethanol, but in both cases, three different types of surrogates, but in all cases, the low temperature heat release was over predicted. So this is, heat release rate is not a common target that's actually used to test mechanisms, but I suppose I might put in a bid to include it as a target, because I think it's telling us something different from ignition delay times. I thought I was going to have quite a lot of time today, but probably not. I think I might skip this bit about categorizing fuels. I think the only point I wanted to make here was that really, there's a lot of people complaining about using basic octane numbers now to categorize fuels, but the octane index is an extension here that was developed by Cal Gatti to give us a slightly more useful way of extrapolating information on the NOx suppression or anti-NOx qualities of a fuel. And the octane index is related to the sensitivity of the octane number. So we're moving forward, I suppose, and moving away from octane numbers, more towards using detailed information on ignition delay times and using octane sensitivity, which is ROM minus MON, as a way of better categorizing fuels for modern engine conditions. I'm going to skip through how we measure. So we've got ways of experimentally monitoring octane number and cetane number, but what if we could actually predict the auto-ignition behavior of fuels across all temperatures and pressures? If we can do that, then surely we can do better than just using simple octane numbers. And so, there is an interest then in developing detailed models that we can then use to predict NOx resistance over very broad ranges of conditions. I don't know. I mean, I guess I'm just asking the question. There's a lot of effort goes into developing accurate models, right? developing the mechanism, which I've talked about today, and then populating it with high fidelity parameters for our rate coefficients and for our thermodynamic data. Is that what, should we be doing that, or should we just bung everything into an ignition quality tester and see how it burns, or even bung it into an engine and see how it burns? I think, it's interesting to do all these things, but we should be getting to the stage now where at least we're trying to bring all this together. So that's, I guess, what several groups are trying to do now, I think, is to bring together experiments that are actually in real devices with an understanding that we're getting from the development of models. In all honesty, it's just easier to bung the fuels into an engine and see what happens. That's probably not quite as interesting. So want to mention a few other techniques that we use for validating our models that might be relevant under different temperature and pressure conditions. So shock tubes actually, we can use shock tubes for ignition delay time measurements, but we can also use them for species profiling. Historically, they've been utilized more for high temperature investigations, but actually shock tubes are now being used for lower temperature investigations as well. But I think the reaction time is perhaps a limitation on looking at longer ignition delays. So for shock tubes, we're getting good information at the higher temperature regime. If we couple that with rapid compression machine measurements, then we should be able to cover the whole of the temperature and pressure regime. I'm not going to say too much about shock tubes, because I mentioned them yesterday already. We can also couple our shock tubes then with time of flight mass spec and gas chromatography to get speciation. And actually, someone reminded me yesterday after the question about shock tubes that actually the new developments in shock tubes, we were talking about Rob Tranter at Argonne, are actually doing now time-dependent speciation through the ignition. From a point of view of alternative fuels, I think the aerosol shock tube is a very useful development. So this is allowing now us to investigate ignition delay times for longer chain length fuels, which are not gaseous, and therefore we have to vaporize them using liquid aerosols. So aerosol shock tubes are allowing us to look at ignition delay times for example, advanced biofuels or biodiesels and things like this. So low vapor pressure fuels like long chain hydrocarbons. So importantly here, we need a uniform spatial distribution of the aerosol, and we ideally would need a uniform or a narrow distribution at least of this aerosol size range to get uniform evaporation, to get good mixtures in the shock tube. Okay, so initially the technique was tested for long-chain alkanes like endodecane and maybe jet fuel, and more recently for fatty acid methyl esters, which are related to biodiesel blends. So there's a lot of really useful data here. So methyl linoleate on the left and methyl oleate are two possible components of biodiesel. And we've got quite high fidelity data on the ignition delays over a range of temperatures here. Okay, so you can see we don't get quite into the low temperature regime that we might see with the RCM, but also interesting, I suppose, about this plot is that we see relatively Arrhenius behavior from these long chain biofuels. Historically, speciation profiles, well, over many decades have been obtained from jet stirred reactors. Actually, at Leeds in chemistry, we used to have quite a big program in jet stir reactors. We even had a glass blower that used to blow these things in the lab, so that was always fun to watch. So these are flow reactors, so they're not closed reactors, flow reactors, and they can give us information about reactants and products over a range of temperatures when we're operating them at steady state, but they're also actually used to look at oscillatory conditions. So actually, as part of my PhD, going back quite a long way, I actually looked at oscillatory hydrogen ignition from a flow reactor from experiments that were done in the lab at Leeds. And actually, I don't know whether oscillations are coming back into fashion. They're quite a stringent test of a mechanism. In order to be, you have to have pretty good chemical mechanism in order to be able to reproduce the period of oscillation and the types of oscillations that you see in these systems. It's more fun than looking at steady state, I guess, from a visual point of view. So I guess the key features that are important in terms of a jet stir reactor are going to be that we're trying to enhance we're trying to enhance mixing to get homogeneous conditions in the reactor. So inhomogeneities are going to limit their usefulness in terms of validating with zero-dimensional models. So some designs will have used stirrers in the past, but I think turbulent mixing through jets is perhaps a better way to go. Preheating of the mixture is going to improve the temperature homogeneity. And I guess historically these were mainly low-pressure reactors, but quartz reactors encased in a pressure-resistant jacket are now allowing some measurements in flow reactors at higher pressures. And they're actually relatively simple to model. I showed you the equations on Monday for flow reactors, so zero-dimensional models we can include, very complex chemistry. They're usually operated isothermally, but caveats to this are that we need to understand the heat losses, so we need to have some kind of understanding of the heat transfer coefficient through the walls of the vessel. And actually this issue about the interaction with radicals from our chemical scheme to the walls is also important. And usually experimentally the vessel will be coated to try and limit the wall reactions. But it's still possible that particularly slower radicals like HO2 might diffuse to the wall and be important. So if you're trying to validate your chemical mechanism against a particular facility device, it's not just the chemical mechanism that you need to think about. You need to think about the other physics or physical aspects of the reactor that you might need to represent in your model, and that also might be uncertain. The residence time, of course, is also of relevance for the jet stir reactor. So we represent it as a scalar number, but actual fact, probably a distribution of residence times that we're representing by an average. Okay, so there are some physical things to watch out for when you're trying to validate your models. Okay, so jet stir reactors have also really moved on. They've quite, well, not that recently, but over the recent years been coupled with synchrotron, or advanced light sources, and UV photoionization, mass spectrometry for detecting intermediates that we didn't used to be able to identify from simple gas chromatography measurements. So there have been some quite interesting papers on detecting key intermediates from low temperature pathways like ketohydroperoxides and enols by coupling jet stir reactors with mass spectrometry information from tunable light sources like the synchrotron. Okay, so again, these provide another means by which we can validate our models. So this is actually some work that we did in collaboration with CNRS, Frederic Baton-Leclerc's group there. So we were looking at butane, and the model simulations here, including uncertainties in the model, are the blue curves, and the red are the experimental measurements. So you can see the model's pretty good at predicting the basic fuel loss, including this NTC region, slightly underestimating that low temperature peak in formaldehyde, and butene was the bigger problem that we saw here, so overestimating concentrations there. So again, it's showing us really where our mechanism is failing. So one of the points that I want to make, I don't know if I might reiterate this on Friday, is that these different experimental targets that we're using are likely to be testing different aspects of our chemistry. And by carrying out sensitivity analysis, we can get information on what aspects of our model is the experiment going to test. And actually, by the end of the week, I hope I'll make the point that actually I kind of think before we do experiments, we should model them first and get an idea of what part of our kinetic model they are likely to constrain. That makes sense. I'll try and say it a different way. So there's two examples here. One is the ignition delay time. And on the right here, we've got the basic fuel. And the blue is indicating sensitivity to fuel-specific reactions in the mechanism. Okay, so for this particular system, you know, in the low temperature in the NTC region, these will be the typical low temperature branching routes that we're used to seeing. As we move to high temperatures, the red is indicating that the sensitivity of the predicted ignition delay times is mainly due to reaction rates in the base chemistry, so the C2 chemistry. Okay. So for butane measurements, the sensitivity analysis is suggesting no sensitivity at all to the fuel-specific reactions, and that the sensitivities are all coming from the base scheme. Might be counterintuitive, I suppose, but that is what the analysis showed. So this is another example, I guess, of looking for a particular fuel, N-butanol in this case, from some of Mani Sarathi's work, at sensitivity of N-butanol. So it's a high temperature study, this, but sensitivity of N-butanol predictions to reactions at the top, and sensitivity in an opposed flow diffusion flame at the bottom. You can see that these two different reaction setups are giving us sensitivities to different reactions in this scheme. So at the top, we're seeing a very high sensitivity to small molecule chemistry. So in this particular case, the decomposition of HCO to H and CO. Whereas in the bottom, we're seeing actual fuel-specific reactions cropping up in the sensitivities. Okay, so I will talk later in the week about optimization, about using all these experiments to try and optimize, to reduce our uncertainties in the model. And if we actually do these simulations and carry out sensitivity analysis, what this is saying is, you know, if we optimize according to the jet stir reactor data at the top, then we've got most information about the small molecule chemistry. If we optimize from using data from the opposed flow diffusion flame, we've got more information about the fuel-specific abstractions. And in this case, it's actually the abstraction by hydrogen, which crops up several times. So that's different from what we get from the low temperature experimental data. So each of these different sets of experiments is going to constrain a different aspect of the model. So what we should be doing is not fitting to small sets of data. We should be optimizing across as much data as we can gather, because each different data set will be sensitive to a different aspect of the model. Makes sense. I guess what I'm saying is I'm trying to argue against tuning to specific data sets again, really. So unless you have, 100% sensitivity to a single parameter, in which case then you can do it. That we really mainly get from kinetics experiments where we've deliberately tried to isolate that parameter. We don't tend to get that from these bulk experiments. There always is more than one parameter involved. Okay, the last, I think it's the last. Oh no, it's not the last. So variable flow reactors. So there's one here at Princeton. So Fred Dreyer has developed a variable pressure flow reactor over many years. So this is basically a high temperature facility that's operated at atmospheric pressure, can access a wide range of conditions from low temperatures as low as 550 up to 1200 K, actually atmospheres beyond atmospheric pressure up to 20 atmospheres. So the idea here is that we get rapid mixing within the diffuser section, which gives us a quasi-steady reaction along the length of the reactor. So we can sample from this reactor to get species measurements. And we actually did some comparisons for DME oxidation against this flow reactor data. Okay, so this is just an example of data from the Princeton flow reactor for dimethyl ether. And what we tried to do here was, again, a full uncertainty study from various different DME models. What we showed was that actually, for our mechanism, we really had to push parameters to the edge of their ranges to overlap with this experimental data. So the box and whiskers are showing the uncertainties in our predictions that are based on the uncertainties within the mechanism. So, this is a log scale. The uncertainties are very large. And yet, even so, to predict things like formaldehyde, we had to push parameters right to the edge of their uncertainty range in order to overlap with the experimental data. So I don't know what that suggests. It suggests that maybe it's true that the model is very uncertain. It might also suggest that there were missing pathways within the model, because if we don't see any if we include large uncertainties in our model, but we still don't see overlap with the experimental data, it might suggest that we've got something missing in terms of pathways. And so it's still useful knowledge. Okay, maybe this is a bit too much at this time of the day. This is another one of those global sensitivity plots. But again, we do see a small number of reactions that basically, their uncertainties contribute really to the uncertainties in our predictions. So predictions of methyl formate particularly were interesting. And actually, this all comes down again to low temperature fuel specific chemistry. So perhaps that's probably at 5:30. That's enough to say about that plot. If anyone's got questions, I can go through it in detail. So as I mentioned earlier, I think the use of advanced light sources has made a step forward really in terms of our ability, well not mine, our collectively ability to identify species, intermediate species that we didn't used to be able to see experimentally. So this is an example of actually quantified measurements of ketohydroperoxides during DME combustion. So it's molecular beam mass spectrometry with a tunable synchrotron generated light source. And that allows us to identify different isomers within the mechanism, and it allowed the quantification of profiles for 17 different components in the mechanism, including key intermediates in the low temperature oxidation of DME. So again, though, what it does is it highlights the differences between the measurements and the ability of the model to predict these concentrations across different temperatures. So although this looks like it's good agreement, actually the simulations have been divided by 6 to fit them on the plot. So they're over-predicting by a factor of 6 in this case. So again, it's highlighting deficiencies in our model. So I guess the final set of validation data tools that we might use are laminar burning velocities. Laminar burning velocity, I think if you were at this morning's session, you probably have heard a lot about this morning. Basically, they're a measure of how fast reactants are moving into the flame zone in a moving frame of reference. If we have something like a spherically expanding flame, then we have to, so what we're actually measuring, I suppose, is the flame speed, and then we have to back out the laminar burning velocity relative to the moving flame front. So flame speeds are measured relative to a fixed point, and the burning velocities are usually, or should be measured relative to the unburnt gas. And so there was, Professor Matalon discussed that in detail this morning. Why do laminar burning velocities matter? So this is quite a nice illustration of that from Fokion Agorphopoulos. I think I nicked it from a presentation actually rather than a paper. But what this is showing is that if we are able to predict the laminar burning velocities for our fuel oxidizer mixtures, then that means that we're able to predict extinction events for practical devices. So what this is showing here is that the prediction of extinction factors shows the same sensitivity, or the sensitivity to the same reactions as does the laminar burning velocity. So if your model is able to predict laminar burning velocities, then that shows that these reactions are well constrained, and that's the same reactions that we need to constrain accurately to predict extinction. Okay, so that's kind of connecting a fundamental property, I suppose, to a property that's important in practical devices like gas turbines. Okay, so the plots there show similar characteristics for 2 different flames. Measuring laminar burning velocities. Historically, they were measured in Bunsen flames, basically. Actually, this is probably one of the lowest accuracy measurements of laminar burning velocity. It's not really used anymore, but some of the older data might come from this type of study. Basically, the laminar burning velocity here, extracting that from the Bunsen flame, means being able to measure the angle here of the flame cone, because what we want is the burning velocity which is normal to the flame surface. So there are experimental difficulties in measuring that angle, and we also might see possible influences of flame stretch and differential diffusion of reactant species that affect this measurement. Okay, so historical measurements might use this method, but it's not really used commonly anymore. The spherically expanding flame, or the bomb, is another method in which we can measure laminar and turbulent burning velocities, actually. But again, this is not a direct measurement. For the most part now, we're using Schlieren photography to look at the progress of the flame front. Then, I think as explained this morning, we have to, well, flame stretch is going to be of importance, and we have to extrapolate to zero stretch to produce laminar burning velocities. Okay, so for some fuels as well, we can start to see cellularity, particularly for hydrogen flames, for example, which is going to have an influence. So we've really got to be careful, I think, that we're extrapolating the right sets of data to produce reliable laminar burning velocities from the bomb. But the advantage of the bomb is, first of all, that we can go to very high pressures in these devices. And secondly, Leeds is one example, I think, where, I'm sure there are others as well, where we can actually control the turbulence inside the bomb, so we can measure turbulent burning velocities at different root mean square velocities. The flat flame burner, or using a heat flux method, is perhaps, atmospheric pressure at least, the highest accuracy method of calculating the laminar burning velocity. Again, though, this is not a direct measurement. There has to be some interpolation to get the laminar burning velocity from this device. I've put a link here to a video that is an animated explanation of this, but I probably haven't got time to show it, but have a watch of that. But what we're trying to do in this experimental setup is to produce adiabatic conditions. So when the gas inlet velocity is less than the laminar burning velocity, the flame will be stabilized on the burner, and as a result, we're going to get heat loss from the flame to the burner plate, which is larger than the heat gain of the gas mixture from the burner plate. So that's a non-adiabatic condition. If we increase the gas inlet velocity to be greater than the laminar burning velocity, then the heat gain from the burner plate is going to be larger than the heat loss of the flame. So again, that's a non-adiabatic situation. So the adiabatic situation will occur when the gas inflow rate is equivalent to the laminar burning velocity. And in this case, the temperature will be flat across the profile of the flame. So one of the ways in which we do this is to continuously vary the inlet velocity until we get a flat temperature profile across the burner plate. And then we will know that the inlet velocity is equal to the laminar burning velocity. Difficult to do, so interpolation methods are used. So temperature profiles are taken at various points across the flat flame, and then we can plot the temperature profile as a function of radial position for various different burning velocities. Okay, so the slope here is given by alpha, and you can see that in some circumstances the slope is positive, some negative. None of these conditions gives us a flat temperature profile. But what we can do is plot that gradient against the unburnt gas velocity. Although our measurements didn't actually hit adiabatic conditions, we can use this this straight line to interpolate to a zero gradient, and that will give us the laminar burning velocity. Okay, so again, it's not a direct method, and the accuracy of this method is going to depend really on having a flat flame across this diffusion burner. We can also use counterflow flames. So again, here the intention is to get a region at least of the flat flame. And the advantage of using counterflow flames is that also we can sample from these and get species profiles as well as laminar burning velocities. What we want to do is get flat flame conditions so that we can simplify the physics here, so where all of our properties are only going to be a function of the axial distance. So we can model that with a 1D simulation. So To summarise then, all of the methods for laminar burning velocities are not using a direct measurement. There's some kind of processing that has to be done, either interpolation of temperature gradients or extrapolations to zero stretch, etc. And so we do see variability between different types of experiments, and there's an inherent level of uncertainty in laminar burning velocity measurements. I think for certain situations, direct numerical simulation might help with the interpretation of some of these measurements. And so if you're interested in this topic, think in the reference list, I've given the link to Fokyon's presentation on this. It's just quite interesting. Okay, so we can see that basically in for hydrogen air, we've got quite some variability of around 50 centimeters per second at the peak in terms of the uncertainties here. And actually from that figure, it does look like the uncertainties are going to be higher at the higher equivalence ratios. But there was a paper by Professor Law that suggested that actually we should be plotting the velocities against a normalized equivalence ratio, and that gives a better representation of the uncertainties across the equivalence ratio range, and actually shows that you know, the uncertainties are present across the whole range of equivalence ratios. Just in case didn't spot the magnitude of the burning velocities for hydrogen, I'm just showing a comparison here between the flame speeds for hydrogen compared to methane. Again, you know, orders of magnitude difference, or nearly 2 orders of magnitude difference here. So hydrogen burns very quickly compared to methane, which is, of course, something that we have to think about in terms of designing devices for hydrogen. Okay. 3 minutes. Okay, so overall then, we can get quite a lot of information from laminar flames. For high pressures, we would be using spherically expanding flames in bomb-type situation. We get laminar burning velocities and turbulent burning velocities, in fact. From flat flames, we can get burning velocities. We can also get extinction and ignition limits. And, well, we can try to get chemical speciation. If we move to lower pressures, chemical speciation gets a little bit easier because we stretch the flame, and it's easier to do accurate sampling at low pressure conditions. Yeah, I think I might have to just skip through this. That's not basically what I was trying to show was, well, let me just make one final point. So here really we're testing the high temperature part of our mechanisms when we're comparing our models against flame speed or burning velocity data. If we do sensitivity analysis, this is for an N-butanol air flame, we don't really see any fuel-specific reactions here. So actually it's the chain branching reaction from the hydrogen mechanism which dominates. So high temperature data tends to be testing the base part of our mechanisms rather than fuel-specific reactions. Well, okay, you know, look at the detail, I guess, if you're interested, but basically what I'm saying here is the same thing, that the flame speed sensitivities are dominated by the small molecule chemistry. I just want to put this in as a final point, and then I'll skip to the conclusion slide. The advantages of using multiple targets, well, there are advantages to using multiple targets. And one example which shows that quite clearly is looking at N-pentane ignition and the ability of our models to predict cyclic ether formation as part of the low temperature pathways. So here, a broad range of experimental data was brought to bear, so ignition delay times, jet stir reactor data, and these were captured quite well by the model. But what the data shows is that cyclic ether mole fractions are predicted very poorly, and that led to the requirements for an update in the rate of their formation from the QOH species. Okay, so this is showing improvements in the cyclic ether formation that were achieved from applying a high level of theory to the rate constants for their formation from QOH. So I think the original data came from a low-level composite method, CBS-QP3, but actually that was insufficient to predict their concentrations accurately, and a higher level of theory was required. So a high level of theory gave significant improvement in the prediction of those two major cyclic ether compounds. I think I'm going to skip to the final slide now. So I guess the take-home points are that each type of experimental target that we use to test a chemical model could be testing our model in different ways. And so we need to compare our models against a broad range of targets to test different parts of the mechanism. Sensitivity analysis offers us a way of identifying, for our given experiment, what part of the mechanism the experiment is actually testing. And in an optimization situation, that also means what part of the mechanism the experiment might constrain. So, for example, ignition delay times really only require an accurate prediction of the relative rate of branching to termination routes. So it's only dependent really on a few reaction rates in the model. Laminar burning velocity measurements add a high temperature target, but actually they're mainly sensitive to the base chemistry, to the small molecule chemistry in our schemes. And if we really want to test the prediction of intermediates in our chemical schemes, then we need speciation measurements. And these are now expanding in their scope from shock tubes, from RCMs, from jet stove reactors. And quite often they highlight potentially missing pathways or highly uncertain rate constants in our mechanisms. I guess the final point I want to make, which is going to feed into Friday's lecture, is that we expect experimentalists to give us error bars on their data, but in general, we're not very good at doing that from our models, in fact. And maybe one of the reasons we don't do it is because actually there's key uncertainties in the models, and the error bars are sometimes quite large. So seeking methods to reduce the uncertainty in our models is quite an important step. Right, that was a lot to get through today. Thanks, everyone. That's everything for today.